Hey everyone, this is a general framework for randomized benchmarking. The paper that this talk was based on was written in collaboration with Ingo, Emilio, Albert, and Jens, and you can find it on the archive over here. All right, let's get to it. So what is randomized benchmarking? Randomized benchmarking is sort of in some sense, the industry standard for quantifying the quality of a quantum gate in a noisy quantum computer. And, it's been around for a decade, and there's been hundreds of experimental papers that use this particular protocol to sort of quantify fidelities, up to the point where I think if you see an average fidelity in an experimental paper, it's usually generated by some kind of randomized benchmarking procedure. So, as I said, it's a protocol for estimating the quality of quantum operations. And the way it does that, it does this in sort of a rather ingenious way, which is to say, we're not going to quantify the fidelity of a single circuit, we're going to quantify the fidelity of a set of circuits and sort of calculate the average fidelity. So we're going to apply quantum circuits from this set at random, and we're going to increase the lengths of these sequences, and we're going to track the increase of error. And this allows you to get an estimate of the quality of your gates independent of any error you might have made in preparing a starting state or measuring at the end of a sequence. And this is nice because typically the error of a quantum gate is quite a lot smaller and also caused by different things than the error in state preparation and measurement. So this is one of the reasons that it's sort of a popular protocol. And the other one is that it's efficient, both sort of in practice and in the computer science sense, that you can, in principle, scale this protocol using a polynomial amount of resources to sort of a large number of qubits. And so these are the reasons that it's sort of nice. And now I've told you what it's for, I haven't really told you how it works exactly. So when I say randomized benchmarking, I sort of mean a set of protocols that all have roughly the same structure, and they all have roughly the following structure. Namely, you prepare some starting state rho that you don't particularly care about what it is, because again, we're sort of state preparation and measurement independent. You define some set of quantum circuits or quantum gates, and then you draw at random sequences of length m, so G1 to Gm, from this set, and then you apply them to your gate. And then you compute, and this is already putting some structural constraints on your set, you compute a global inverse for this G1 times Gm, and then you apply this as well. So if you've done everything perfectly, you're applying the identity. And then you measure in some POVM, usually some two-component POVM, but it could be more general. And then you sort of do this for a bunch of random sequences, gather all the statistics, and average it out. And sort of the intuitive idea is because these sequences accrue error multiplicatively, you should see roughly an exponential decay in this data, and you sort of hear some sort of simulated example data where you see the exponential decay on average. And then from the rate of decay of this exponential, you hope to abstract some quality of your gates. And that's sort of the generic idea, which has been around for, I think, 15 years or so. And over, the last 15 years, people have developed at least 35, to my knowledge, different versions of this protocol using different gate sets and different post-processing methods and different initial and ending gates and states. And so this is sort of a well-developed body of work, and there's lots of experimental work around this as well. But still there's a lot of confusion, or at least a fair amount of argument about what is precisely necessary for randomized benchmarking to work. Because this exponential that I showed you is not guaranteed. It's incumbent upon the structure of your set, but also upon assumptions that you make on the behavior of your underlying device. It has to work sufficiently well for you to be able to do this experiment in the first place. And there's sort of confusion about what the boundaries are. And the goal of the paper, which we sort of set out to write, which you can find in the archive, was really to try and clear up as much of this confusion as possible. We didn't quite succeed, but we did do, I think, a lot of interesting things. So we did sort of these 5 things, and I'm going to talk about 3 of them because, again, it's a very long paper. So we've sort of given a general framework or sort of a meta-RB protocol that you can sort of, from which you can retrieve all sort of previous versions of randomized benchmarking. And then we've proven rigorously that in sort of a wide spectrum of cases, this meta-RB protocol behaves the way it should. And I'll get into a little bit more detail on that. And then we also give a really, I think, a really nice general method for post-processing data that comes out of randomized benchmarking and do some cool tricks there. And then we also did some cool work on doing proper fittings of these exponential decays and discussed sort of what it means to be a randomized benchmarking output and how that relates to fidelity. But given that we don't have a lot of time, I'm not going to get into those too much. So if you want to know about these, you should just go to the paper. All right, let's do this. So let's talk about this sort of meta-RB protocol. And this is really sort of a more of a collection effort. It's an effort to write down in sort of a rigorous way what we mean by randomized benchmarking. And what we mean by randomized benchmarking, and you could disagree with this, is a protocol that is composed of the following set of inputs. So this is how you describe it. These are the things that sort of the user specifies. The first thing you specify is a group. Now this is already controversial because some people do randomized benchmarking without groups, but for our purposes we're going to stick to our gate set forming some kind of group. The paradigmatic example here is of course the Clifford group, so that's sort of the thing you can keep in mind. And then the second thing is that you should also specify a way to embed this group into the space of unitaries, or more generally in the space of superoperators. And this is quantified by the idea of a reference representation. And typically this is, you don't even really think about it, it's just sort of the normal UU dagger, where U is the circuit associated to your group element G. But it could in principle be something else, and people have done randomized benchmarking with other types of representations, so we're going to leave it open. Then there's a POVM that you measure on the end. This isn't really super important, but we have to specify it. There's also an initial state. And then, there's also a set of sequence lengths, where you are going to gather your data. And then finally, we make this sort of our own idiosyncratic addition that we think is important, is we are going to add something we call an end gate. And normally, as I said before, randomized benchmarking, people compile their sequences up to the identity. But in principle, you don't have to do this. You could compile your sequence up to some other gate. And this is important for post-processing methods. So we're going to keep it in explicitly, and we're going to use it later. But if you're confused by this, you can just imagine this to be the identity at all times. And then, so these are the things that you specify. And then from your quantum computer, and mind you, this is already an assumption, but it's sort of I think, a reasonable assumption to make, at least if you want to prove theorems, which is that your computer provides for each element in your group, so for each circuit you implement a superoperator, so a CPTP map that sort of encodes the noise that happens on this circuit. So note that this is not a gate-independent noise assumption. It's much broader than that, but it's also not the most general possible thing. There's no time or context dependence here. But we think this is sort of a reasonable model to prove theorems in. And then given all of these things, what comes out of your experiment is a list of probabilities that depend on your POVM and also your initial state and your end gate and your sequence length. And often I'm going to shorten this to just P of M because the M is sort of the relevant part. And the way, given all of these things, the way you implement randomized benchmarking is, as I said before, you prepare some starting state, you apply randomly G1 to GM, you compute the inverse, you add the end gate, and it's important that you compile it in. So you compile up to some end gate, you apply that, you measure, and then you gather this probability data and you average over all of like a whole bunch of random sequences. So that's sort of a generic randomized benchmarking experiment. And by filling in these things, you can recover all of these 35 plus protocols that people have proposed before. So now we can get to sort of proving theorems for all of these protocols at the same time, which I think is kind of neat. So you have this set of probabilities, and now we are going to want to sort of make claims about how these probabilities behave. And that's what we're going to do now. This is like, what's the shape of this randomized benchmarking data? And the sort of folklore truism of randomized benchmarking, and the reason I emphasized this representation, this reference representation so much, is that representation structure defines the data structure. And the paradigmatic example of this is the sort of standard representation of the Clifford group, which in its standard representation has two irreducible sub-representations, one spanned by the identity and one spanned by everything else. And the direct consequence of this is that under reasonable assumptions, the probability data is a linear combination of two exponentials, one of which happens to be a constant due to CPTP-ness. But the second one is sort of your exponential decay, and this is the thing that you extract, and you can relate this to the fidelity. And now people have sort of looked at this more broadly and realized that in general, if you have some arbitrary group gate set with some more complex representation, that's a linear combination, that's a direct sum of inequivalent irreducible representations, then your data does not look like a single exponential decay. It looks like a linear combination of exponential decays that correspond exactly to all of these irreducible representations. So if you have this, you get this under reasonable assumptions, hopefully, where you can think of lambda I as sort of the fidelity with respect to this particular subspace, and there's always some sort of weighted average of these lambdas that allows you to recover the sort of standard average fidelity. So that's sort of the general truism. So the claim is, as I said, this isn't necessarily guaranteed by the structure of randomized benchmarking itself. You have to make some assumption on your gates, on the way the noise behaves. And sort of the folklore idea, which has been proven rigorously in some cases, is that as long as this implementation is somehow, the implementation, so the thing you actually do, is somehow close to the thing you want to do, the reference representation, then this sort of generic linear combination of exponentials formula holds at least up to a very good approximation. And this has been proven rigorously in some cases. We'll get back to that. But we want to sort of prove this generically, and we also want to elucidate the precise meaning of close. So how can we justify this claim in general is really sort of our first main statement. And this leads us to what I would call a theorem. So this is in some sense theorem one. It says if you consider a randomized benchmarking procedure with some group G, which has some implementation map phi and some reference representation that is a direct sum of irreducible representations that importantly show up with some multiplicity. This will come back later. So not all of the irreducible representations are necessarily unique. So this is sort of the most general case. By Maschke's lemma, this is always true for a representation if you can write it like this. And then you make an assumption on the behavior of your noise. And you're going to make the assumption that on average, the diamond distance between your implementation and sort of the ideal implementation is small. And it is actually important that you pick the diamond distance here, or at least some sort of worst case measure of distance. If you pick something like average fidelity, this theorem will fail. I'm not going to get into that too much. You can read the details in the paper. If this is true, then you can prove sort of rigorously that the probability output data of randomized benchmarking, so this has to be a GN, is going to be close to a linear combination of matrix exponentials, and this is important here. These M's are matrices, and the size of these matrices is exactly given by these multiplicities. So if you don't have multiplicities, you recover sort of the linear combination of exponential standard. And you get this approximation up to something that is exponentially small in M and delta, which is really cool because that means for like even moderately sized M and moderately sized delta, you get an extremely good approximation. And interestingly, you can think of these M's as sort of the frequencies of this signal, and I'll make this more precise in a minute. We also have a non-uniform version of this theorem where you don't pick your sequences uniformly at random, but your due to some other distribution, but the error behavior is notably worse. But this is something interesting if you're into these kind of particular things. So how do we prove this theorem? How do we get to this sort of rigorous statement? Well, it's really a combination of two things that have been realized earlier, and some fairly tedious to make rigorous perturbation theory. So the first sort of thing that we used is this beautiful idea by Merkel, Pritchett, and Fong, which is that randomized benchmarking can be thought of as an n-fold convolution of this sort of matrix-valued map for a suitable notion of convolution. And where there is convolution, there is Fourier transform, and Fourier transforms map convolutions to powers. So what this really means is that this P of M data can be thought of as the m-fold power of some matrix that is the Fourier transform of phi, taken at some particular location, so the inner product with some other matrix that is defined by rho and pi. So this is our first major ingredient. And then the second major ingredient is due to Jill Wellman, who sort of implicitly realized in his, when he proved a rigorous version of what we're saying for just the Clifford group, he sort of implicitly realized that a good norm on this Fourier space is this average over the diamond norm. And that this behaves really as a nice submultiplicative matrix norm on this space of Fourier operators that are dependent on phi. And if you take both of these things, then you can say, aha, this is a trace of some matrix to the power m. So you can say, okay, we can think of f of phi as a small perturbation around the ideal representation in this, where I mean small in this distance. And then if you look at it a little bit more closely, you'll realize that the Fourier transforms of ideal representations are always projectors with their rank given by the multiplicity of an irreducible representation. So f omega is a sum of orthogonal projectors of a fixed rank. And f phi is sort of a perturbation of that, which means that sort of generically f phi has a few very large eigenvalues and then a whole bunch of really small ones. And if you take an m-fold power, these really small ones are just going to disappear. And then the complicated bit is then using non-normal perturbation theory, because these matrices aren't necessarily Hermitian, so you have to be a little bit careful, is proving that this is sort of rigorously true in terms of a norm that is sort of physically relevant, even though it's worst case. And that's sort of like getting this completely right for all randomized benchmarking protocols in complete generality is sort of the first major contribution. So that settles sort of the debate of your randomized benchmarking data. And now once you have this data and you've sort of argued that it's a linear combination of maybe matrix exponentials, what do you do with it? Well, you are going to fit these exponential decays and then extract some quality measure of your gate set. And of course, in general, this data looks like a linear combination of matrix exponentials, where this can be quite a large sum. So even if you gather this data for different m's, the problem is that this fitting problem, even if these things are really numbers, so they're not matrices, because that makes the problem worse, even if these things are just a linear combination of exponentials, this problem is extremely ill-conditioned. So for more than a few exponentials, you're just not going to get anywhere. So the question is, can we take our randomized benchmarking data and isolate these single decays in a sort of rigorous manner so that we can just fit a single exponential, which we know how to do? And I've said before in this Fourier picture, it's sort of useful to think of these m's as frequencies associated to particular representations, where your representations are sort of your ground notes of your system. And if you think about it like that, you can start thinking about basically doing signal processing and saying, okay, can I define sort of a filter function that isolates a particular frequency? And it turns out that here, this sort of end gate is really key, because this makes P of G into a function on the group to the real line. And this is a well-defined object. It's called the group algebra. And inside this group algebra, you can sort of do Fourier analysis. And in particular, you can sort of take the inner product or the average over end gates with some other function that depends on your irreducible representations. And if you pick this function right, and I'll get into this, what you can do is you can sort of exactly isolate one of these exponentials, which is hopefully, if you pick your multiplicities right, it's going to be a single exponential. And then you can sort of fit it rigorously. And this is a very broad idea. And there's lots of people that have sort of done this, a version of this, without being so explicit about the group algebra picture, to isolate single exponentials. Most notably here, I think sort of unexpectedly, is that linear cost entropy benchmarking, which the Google team used to sort of benchmark their supremacy experiment, is that this is really an example of standard randomized benchmarking with this sort of signal processing based post-processing step. So that's an interesting sort of thing that falls out of the math here. So you can think of linear cost entropy or randomized benchmarking as just randomized benchmarking plus a post-processing step, plus or minus some details, of course. So how do we actually find these Fs? Well, it turns out that there's sort of a surprisingly generic way of doing this, which comes from the fact that this space of functions from the group to the real line or the complex line, this is a vector space. It's an algebra, and it's sort of, if you tensor it up, you get this Fourier space. And it turns out that matrix elements of irreducible representations precisely form an orthonormal basis for this Fourier space, which means that if you, with respect to sort of a sum over the group inner product, which means that if you take an average over the group and you sort of take some element of your implementation map and you sort of correlate it, you take the inner product with some element of an irreducible representation, you get the Fourier transform evaluated precisely at that irreducible representation, which means you exactly isolate one of these projectors or everything close to it, which means you isolate a single exponential decay. And this basically is Schur's lemma, or the ground orthogonality theorem, if you please. For compact groups, it's the Peter-Weil theorem. This is sort of well understood group theory, and we can apply it to do randomized benchmarking. So we can basically just pick a, if we want to create one of these correlation functions, what we do is we pick a representation that we want to isolate, and then we just sort of take a matrix element, and we're going to take one that sort of maximally correlates with our data. So we're going to use the POVM and the input state that we've sort of started with to make sort of a maximal correlation. And then we get some K of M, and you can prove under the same assumptions as before that this gives you exactly this single exponential. And that means that you can fit the single exponential. The problem is that it's now not so clear that this K of M is actually efficiently estimable, because we're sort of averaging over a thing that is not necessarily a small object, because you have no real physical bounds on these matrix elements. So can we prove that this is always sort of estimatable in polynomial time? And the answer is not really, because sometimes it's genuinely hard to do, but you can prove some generic theorem. So you can sort of create an estimator by randomly selecting end gates and then measuring, but it's not clear that this estimator has bounded variance. But it turns out that if you assume that your POVM is a 3 design, and this is sort of a bit of a weird technical condition, but that's what we could prove it under. If you prove that if you take that it's a 3 design, then it turns out that this K of M is actually an efficiently estimable thing. And the reason for this is essentially because you can sort of use Weingarten calculus to get your way out of this, to cancel the dimensional factors. And there is probably a sort of strong connection to this recent shadow tomography paper, which is sort of very exciting. And I think like our randomized benchmarking correlation trick and shadow tomography, they sort of really work for the same reason. So it would be cool to sort of figure out more precisely what the connection between these two things is. All right, so those are the things, those are the sort of getting to the end of my talk. So we formulated a general randomized benchmarking scheme, sort of gathering up all possible randomized benchmarking protocols, or at least almost all. There's a few that don't quite fit, but there's a detailed sort of formulation of this in the paper. And then we've proven a sort of general sufficient condition for proper behavior, emphasizing this sort of diamond norm distance. We formulated a general post-processing scheme based on ideas from filtering and sort of Fourier transforms on groups, which is provably efficient if the POVM that you're measuring in is a 3 design, and probably also in other cases. This is a sufficient condition, but certainly not a necessary condition. Interestingly, note that this removes the need for inversion gates in randomized benchmarking. So this is something that I need to be more explicit about, is because once you compile in a random gate at the end, you might as well just do a bunch of random gates, which means you don't have to actually compute the inverse if you do these signal processing methods, which is kind of cool. It's sort of useful for experimentalists. So these sort of signal processing techniques are actually easier to implement because you just implement random sequences and then you do everything else in post-processing. Now the question is, can we take the signal processing analogy further? Can we, do different filtering schemes? Because now we're sort of filtering with a single delta peak almost. So can we do something else? Maybe there's some cool stuff that we can do here. And then finally, so what is the connection between randomized benchmarking and shadow tomography? Are they secretly the same thing? Maybe. It's probably fun to make this concrete and see where sort of the shadow techniques can contribute to randomized benchmarking, where randomized benchmarking can contribute to these shadow techniques, make them more robust or something. So these are all questions that I'm sort of thinking about now. All right, and with that, I'd like to end, and thank you for listening.